Hello, I'm Hedi. I'm presenting Runar Bäckström Foundation. I have honor here to sit here with two wonderful men, and we have given them grant money in year 2022. So can you please introduce yourself and a little bit about your background and who you are?
Okay, well, my name's Ron Zevenhoven. I have a PhD and Master's in Chemical Engineering from Delft, Netherlands. I came here in the 90s for a few years postdoc, but I'm still here. I'm here having a professorship in process engineering. Officially it's engineering, thermodynamics and modeling. So that involves also heat engineering, fluid dynamics, these types of things.
My name is Gopalakrishna, and then I came from India, where I had my bachelor's degree in aeronautical engineering. And then I continued my master's studies in mechanical engineering from the University of Linköping University of Technology in Sweden. During that time, I had a chance to meet my supervisor, Ron Zevenhoven, at an international conference with his previous PhD candidate. So where I got introduced this passive cooling concept. Oh, that was really fascinating. But then my supervisor was quite busy, and then he had other PhD students. And then during COVID time, then I gained contact with my supervisor. Okay, what's the situation now? Can I start my PhD? So then, yes, luckily, he supported me a lot with many applications, and then I got the grant directly from Akademi. So successfully, I landed my PhD here in 2021. So from then, I continued working on passive cooling concept. You see the countries like India, they were really hot. And not only India, there are so many hot countries. Using air condition is really becoming essential each and every day due to this urban heat and whatever. So air conditioning increases this carbon emission. So when we try to bring all this passive cooling into this building to cool the building spaces without electricity, it can save a lot of electricity bill, energy consumption. We can also cut down these carbon emissions. So this is where my motivation comes. Okay, this is really interesting. I wanted to work on. So this is where actually my motivation comes into this project.
One thing we started to think about in around 2005-06 when I was here was what can we do with the greenhouse effect. We know greenhouse effect is giving global warming, climate change, refugee crisis, etc. Big drama. You can write books about that one. But then I thought, what about making use of it? So then I started to consider, okay, what if I would have a double glass window that we all have in our houses? If you would have CO2 in between, would it become really warm? Would the windows explode? The heat from inside the building would be absorbed by the CO2, and what happens then? And then we thought about maybe using that effect to cool, because there are some physical phenomena in the atmosphere that can help us. Something is called the atmospheric window, which is not an object, but it's a range of wavelengths of light or heat, where there is nothing, no molecules, no water, ozone, CO2, oxygen, nitrogen, no molecules in the atmosphere interact with radiation. So then I thought, okay, if we can have a skylight, so a roof window in maybe your bedroom, right? We can maybe send heat from our overheated house or building or office or parked car for that matter, send it straight to space where it belongs. So we counter effect the greenhouse effect because we create basically a stronger greenhouse effect. So we take a window, and part of it, like having just one leak in a boat, a little leak in the boat, your boat will sink. You don't need to take the complete bottom of the boat out to sink. You need a little leak where the long wave radiation can go out. So what we did is we take glass, we put in a section in the skylights we have here. We have a 90 by 40 skylights centimeters, but we have a piece of like 10 by 10 centimeters of a special glass where this radiation can go in, be absorbed by the gas we have in there, and that gas then has the right wavelengths, and if it sees the sky, it will kick it to the universe. If there's no clouds, no water molecules, there's 3 Kelvin up there. Very cold, so that's a big driving force.
Yes.
And then we have the heat where we want it to be, away from Earth.
So basically the objective, the whole concept is to produce cooling without electricity. That is a basic concept. So by using the physics behind it.
But then because of during the daytime, then all this heat comes in. Gopala got the idea. Let's see if with nanoparticles we can selectively keep away all this unnecessary sunlight that is not helping us. So what we should do is cover our skylight, or at least part of it, with these nanoparticles, so that we can get rid of some of this sunlight that we do not want. I think it's at least half of the radiation that the sun gives us that we cannot see. But if it comes into your house, it warms up your house. And then I have to switch on some air conditioning and use electricity for that. And then somewhere else there's a power plant producing CO2 again. So it's just a loop that just keeps spiraling out of control. That's what we have now. You can see also car industry doing the same thing. So for example, some German car manufacturers, they have actually windshields, car windows, that allow visible light to come in from the sun. But the wavelengths there that our eyes cannot see are blocked out, because they will only heat up the interior of the car, and then the air conditioning has to do the work and then burn fuel to get the heat out. So that's energy economy. That's everything we're about after here. And then the question comes, of course, and that was the starting point, how many nanoparticles? If I have this glass, how many nanoparticles do I need? How big do they have to be? 20 nanometers, 30, 50, and what nanoparticles? And then the whole physics becomes complicated. We have, fortunately, physical chemistry in the building. They produce nanoparticles for our catalysis research and things like that. So different type of materials. But then that's this type of research with optics and wavelength dependent measurements. It's not a cheap hobby. So I was very grateful to have some backup in the form of this foundation. And again, we thought that this may go to something patentable, and that was exactly what the foundation wanted to hear.
Have you put yourself a certain timeline, or how this, how I say it?
Productization, maybe.
Yes.
Yeah. Not yet. I mean, it's we have to look at the data still. What's the optimized scale? How much of special glass is needed? How really does it give the best effects?
Yeah, we need to do like design optimization and the material optimization, and we need to balance like the thermal emissivity and the solar reflectance so that it can produce the best output to produce cooling. So this is what we have to work on, have to balance this thermal emissivity and the solar reflectivity, because we are trying to use one single material, which is Cleartron ZNS glass, to optimize two material properties. Two material properties is very critical. One is thermal emissivity and solar reflectance. So simultaneously controlling these two parameters is really challenging. So this is where we really have to work on to optimize nanoparticles, shape, size, and how much coverage of nanoparticles is required to deposit on this Cleartron glass. So we still need to work on this design optimization, and there are some things to be developed more.
Do we then, we don't need air conditioning anymore? Or
less if you're able to cool your house without any effort. If we now have this design, then we have a window and we put in some parts of special glass so that heat can go out, not only in, but the heat can also go out, and then put these nanoparticles on. And that has been the experimental series that we've done this summer.
So we start this experiment around 2 o'clock in the noon, and then we wanted to see how the trend goes when the sun is very intense and when is going back after the sunset. Yeah. So we wanted to look at this trend, how this passive cooling performs exactly.
But we had these very long days here in Finland, and in that respect it would be much easier to take the whole thing to Nairobi and then do a set of tests there, because the conditions are much more stable. And if in Finland now every day is 10 minutes shorter than yesterday, so it goes really fast. And but we got a lot of data, and we have confirmed that ammonia works much better. Ammonia mixed with air works much better than CO2, and we know what gas we want. We know also roughly how much nanoparticles we want.
Yeah.
So how much, because of course you put too many nanoparticles, then you can cover, then it's just paint in your window, you see nothing anymore. So we need a little bit. Now the next phase would be, can we then optimize these nanoparticles so that we do not reflect but absorb the heat and convert to electricity? Because then it becomes more interesting. Then you cool your house and generate electricity for the same house. And or for the neighbor who doesn't have the skylight and runs an old-fashioned air conditioning system. So then you give him or her electricity from your. Yeah, but now we have to see, is this already fancy enough as a commercial product? Is it too dependent on the weather?
But this can be used as a two ways. Like the one is passive cooling skylight, and the other one is like thermal insulator as well. So it can be worked as both.
Yeah, you can insulate this.
Yeah, you can insulate one of the glass material covered with some opaque materials, and then we cannot transmit the heat from building space to the outside. Then definitely it is a thermal insulator. So it can work either in both ways, either as a passive cooling skylight or thermal insulator during winter. Because during winter we wanted to preserve the heat. We don't want to send the heat outside of the building. So.
Yeah.
I want to actually go more to the personal side as well. As we see with the product, there's coming many challenges. So how have you kept yourself motivating by doing what you're doing?
I wanted to obtain my doctorate, and then I wanted to do something good to the society in a way, like the sustainable way. Like we are working on sustainable every time. Because it is very important to, give the clean environment, like whatever the earth, to the next generations. It should be, the clean and green. So that's where every researcher is focusing on. So that's where I keep motivating. Okay, so why would I give up? So yeah, I have so much of support from the friends, like my professors and the colleagues. So if I feel, okay, something low, I can go and talk to them. Okay,
Yes.
Then I just keep motivate. Okay, today and then tomorrow. So why would I give up? No, because this is the path I choose.
Yeah.
So I don't want to give up. Then
So
it can
where
be
do you
patentable.
see the product after 3 to 5 years?
I think it can be possible to take it a full product to the commercialized into the markets. That is one thing. But before that, as I said before, like we need to work on design and optimization. The good thing is maybe if we have a possibility, we can try to tie up with industries like who have a dedicated space to work on to develop the things. So definitely it will be patentable after 3 to 4 years. So it's a commercial product can go into the markets.
I still hope to convince myself in some way or form to put this into my own house, maybe. I have to convince some people that this is a good idea, or at least build a little prototype that I can move around, maybe passive cooling, just that I take to the beach, that I cool my drinks there, and that people start to wonder, what is this? Then this is just this guy there, and his drinks are cold and our drinks are boiling. What's this guy doing? Something like that. The simple. Putting a big hole in my house would be a bit more drama, but something like that. I would like to put together a little prototype, and then via people wondering what's happening here.
Can you say shortly where your product could be applied?
It can be applied in many places like residential buildings and public buildings like hospitals, and it can be implemented in data centers. So, and also it can be implemented in automobiles as one of the application explained by the supervisor, and also in the solar cells. And also you can also use these kind of technology to your clothes. You can just paint these nanoparticles. It can reflect most of the sunlight. I remember like when you came in, you were really warm. So, but if you have such kind of reflective paints on your clothes, which is very transparent, so then you can reflect most of the sunlight, and then you will feel cold during summer. Yeah, there are so many possibilities.
So what has been the part of Runar Bäckström Foundation in advancing your innovation?
Practically, the funding allowed the networking. Gopala attended a couple of conferences, met some people that are very good to talk to, that had some ideas and suggestions. And of course, it's always good because it's two of us, and of course you can have a crazy idea and develop it together, but at some point you become snowblind from what the other is writing, and so you have to have impact with the outside world. And also we were able to purchase things. We need to buy nanoparticles, we need to buy equipment, maybe Gopala wanted to have a bigger piece of glass cover than what they could do in the lab, so we had to develop something for that. And travel funding, of course, to go where you need to be.
How could the foundation better support innovations that promote Finland economy and competitiveness in the future? Or basically how we could do things better?
Yeah, of course, the whole Finnish clean tech, and this is typically what Finland is good at: energy technology and climate clean technology. On the other hand, of course, when you are funding a bunch of people who try to develop something into a patent, it may be very difficult to say, let's once a year organize a seminar, and all those who do some applied physics, we meet and we let them, like we do with PhD students, inform each other how things are going.
And also, I would think that Runar Bäckström can also support the few startups, for example, so that things can move much better and at the faster way.
Yeah.
And also, the Runar Bäckström can also give the funding. Money can be used when a student go abroad, not in Finland, so he can improve the network and get the idea and come back to Finland and try to work more.
Yeah.
So even Runar Bäckström can support students who want to go abroad and do the research for a couple of months and then come back to Finland.
So what advice you would give to young people who are considering a career as innovator or entrepreneur?
Well, one thing I always say to people is figure out what you want to do and what you're good at, and then find a place to do it. So I think one important thing is to go to the place where you can do what you want to do, instead of staying where you are. Figure out what you want to do, and then maybe financially is maybe interesting to say, figure out what you're good at and do nothing else.
Not too afraid to implement any of the ideas. Take risk and move further, and because it's an innovation. Keep your persistence and then work on your things. So
Do you have some tips for keep up the motivation?
it's your passion. And then I would say, like I always say, like to young students, like 3D principle. D, discipline, determination, and dedication.
Yeah.
This is very important for the younger generation. Otherwise, it's very difficult to keep motivating yourself. Yeah.
All right, so what we have here is a prototype with many wires that are there for temperature measurements that wouldn't be in a real prototype. We have a double glass situation here. We have implemented here both in the top glass and in the bottom glass. The distance is about 10 centimeters. We put a little bit of a glass that allows long wavelength radiation to penetrate. So we have asymmetrically two windows where the lower one would take in the heat, long wavelength radiation, into the gas here that absorbs a significant amount of heat. And via the window up here, then the heat will have a contact with the sky and will be able to radiate and go to the sky and maybe even the universe behind it. Now the challenge was already 10 years ago that during the day you will have a lot of light coming in. So what we have figured out with Gopala is that if we take this special glass, which is a zinc sulfide ZNS Cleartron product, has a little section there. If we coat it with a little bit of what you see here as a dispersion of nanoparticles, if you put a little amount of that, roughly 20% coverage, then we are having that on this top glass here, so we are able to reflect a significant amount of the heat that during the daytime would otherwise heat up via the window your room below. And other gases can still be tested, optimization of the nanoparticle amounts and types. And then one objective of the future work is that instead of reflecting a significant amount of solar energy that we do not want, we aim of maybe converting that into electricity.
Ja suomeksi sanotaan, että olette tärkeiden asioiden äärellä. So, thank you so much and I wish you all the best.
Thank you.
Thank you also. Thank you for being here.